biggest subtle misunderstanding. It's about hardware failure. You keep pushing toward, is this about CPU, memory, transistor level failure? Where this goes wrong, you're mixing two different layers: hardware correctness, CPU, MMU bits, language semantics, what the program means. Most runtime errors like uninitialized variables, type errors, do not come from hardware failure. So the runtime error is more of a language semantics. So from the word semantics, it's the, do you call that? It's not syntax, it's the semantics, or like the pattern, or what's the meaning of that syntax when combined. Kind of like a sentence in English or in a language. What's actually happening? Hardware is working perfectly. The program is executing valid instructions. The language runtime decides this state is invalid according to the language rules. So runtime errors are semantic violations, not hardware failures. So a runtime, for example, your program carve out a process. So meaning when your application is in runtime, it is borrowing some part, or it is currently using the CPU. So other processes in the operating system or on your PC is not using the CPU. So basically, if that fails or it exit or your system crash, it means it's a semantic violations. Why this matters later? If you don't separate this cleanly, you'll struggle with type systems, language design, compiler correctness, formal semantics. So in a language design, and then how the compiler actually work, if you don't internalize that, you won't be able to push through that. An initialized variable equal memory issue, partial truth but misleading. You're thinking, is it because memory wasn't initialized? The gap, that's only true in low-level languages like C, but in interpreters like Flux and JavaScript, there's no raw memory access happening. So one initialized variable could be a memory issue when we talk about low-level language like C, because they do have a direct access on memory. But for JavaScript, there's actually no memory access happening. So you can't, like carve or free memory, allocate using malloc and then free it. More precise model in locks. So we have environment is equals to a uninitialized. So in this environment, which is a scope, provided to this variable that you've written, if you have this uninitialized, therefore that's not RAM garbage, it's a logical state in a data structure. So just because you have this code does not mean you're not freeing memory, just like with C. It's just that the structure of your code has incorrect logical state in its data structure now, because it has it variable and initialized. Key correction: an initialized variable is a missing binding or value in a semantic model, not a hardware memory issue. So what it really means is more of a language side, is that when you have an initialized variable, it means you're missing a value that will force the language to make meaning, to make semantic meaning on your model. It's not a hardware memory issue per se, just like with C. So why this matters? Later topics like closures, scope chains, environments, garbage collectors, all depends on these abstractions. So the closures, scope chains, those are more of a language semantics issue, and an environments and garbage collection uh, is more of like a environment and garbage collection is a gray area or rather both sides, because it has a scope with language and it has a scope with memory as well. So those depend on that abstraction. Stack unwinding equal bits popping, almost right, but incomplete. Another thing, background with stack winding, is that the most common security vulnerability is a buffer overflow in memory, in which you overflow the stock that is allocated to the process. Therefore, that process we're able to carve another um, process from OS, and then another memory. Therefore, could execute code that your system are not allowed to do. So that's kind of related to this stock unwinding. So bits popping, you said, is it like a stock data structure? What happens in bits? Yes, it's LIFO. It's still the data structure LIFO. Yes, frames are removed. What's missing? You're taking two data structure only. What matter more is control flow plus instruction pointer. More precise model, each stack frame contains return address, instruction pointer, local variables, execution, context. So the stack frame has a local variables, those primitive data types. Execution context, it's related to environment, to what scope that function are being applied. The return address, so this is related to malloc as well, that returns heap. So malloc, remember, that returns void. That void has a base address, so it is pointer to an address. So it's the same with stock as well. But in stock, usually we have the function name, the variable, and the return address. So when I'm winding, first frame is removed. Now CPU jumps to save instruction pointer. So after that frame is removed, since stock returned the address, therefore CPU knows where to jump next instruction. So this is exactly the instruction pointer we've been discussing inside the machine. Third, run checks for handler and then repeat. So key correction, stock unwinding is not just removing data, it's rewriting the program's control flow path. Also, just because you have this stock like execution, kind of like sequential execution, does not mean that's how the code actually ran, because code when running in memory mimic more of a control flow or if else, because some part of that code is just meant not to be executed unless it meets a certain condition. So it's not a sequential per se, it depends on the user's behavior as well. Another thing is that one of the things that cause this stack or buffer overflow is a user inputs, the application code, the network. So there's a lot of things that could affect the buffer overflow or the stack, or destabilize this stack winding. Number 4, interpreter prevents corrupted logic. Too vague. He said, is the role of interpreter to minimize corrupted business logic. Problem, this is too high level and imprecise. Precise version, the interpreter enforces language invariance. So it's like with the single source of truth of database. Examples, variables must have values, not uninitialized. So I mean some language can do an uninitialized value, but a proper way to use a variable is that it must have a value, because otherwise it will be allocating or it will be consuming some memory resources without actually using it. Operations must have a valid types, so it goes back to how the logic of math must coincide with this. Control flow must be valid. So the control flow, the if else, when this condition should be valid, meaning that when these conditions are met, it means that it follows the overall logic of the app. It won't corrupt, or it won't affect, or it won't result in a side effect that has an invalid types. And the variables must have values inside of those control flow statements. So key correction, it's not about business logic, it's about preserving semantic invariance of the language. So another thing is that you are really trying to enforce the meaning, because you're trying to make sense, or you're trying to enforce a meaning. Otherwise, it's just pure 1010 or bits being executed of the CPU. So what a language does is that you're forcing a language instead of being open for interpretation, because otherwise you won't be able to do what you want to do with the program or with the computer. So that's what really a programming language does. It's more on the semantic side rather than a syntax side. So those syntax could change, but the semantics must be enforced, or must be rigid. It's also the reason why a language took a long time for its semantics to change, because a change in it will also require all of the language or the programs or application that use that programming language to change from the start of its inception. So most successful programming language actually has tight semantics, so it follows the philosophy of software design pattern as well that we've been discussing. So this preserving semantics also is a design pattern. So this is really related, but we're applying the design pattern in a language creation part rather than the program part. So it's still a program. You still create or allows a language through a programming language, but at the same time you're still using the design patterns to create those software. So that's what a software engineer does. So why not just continue? This is your most important gap. You're asking, what if we allow corrupted logic? You're close but missing the formal reason. Current intuition slightly vague, it leads to bugs. Deeper precise reason, continuing execution would violate referential transparency of evaluation, meaning x is equals to a plus b. If a has no value, there's no valid result for this expression. So humans, you may think that you're referencing this in memory and this value of memory. So without those checks, without those firm semantics and logic, we won't be able to see the values that we carve out from memory that we want to show ultimately in our front end, in our LCD, right? So there's no valid result for this expression. So not wrong result, not approximate result, no result exists. Key correction, the program is no longer a valid mathematical or computational function. Why this matters? This connects directly to lambda calculus, functional programming, type theory, compiler correctness. So later, we will discuss how the program mimics really the lambda calculus and the functional programming. So what we're really doing is that we're doing computation here. So it's essential for us to avoid doing this um, referential or violation of referential transparency of evaluation of those expressions. Missing concept, undefined versus unrepresentable. This is a big omission. Two different cases. Undefined JavaScript, let a semicolon value exist, but the value is undefined. Unrepresentable, LOX error, print a semicolon. It will provide an error. No value exists at all because that's not allowed in LOX. Key distinction, case undefined, meaning value exists but empty. Case runtime error, meaning value cannot exist. This distinction is huge in language design. So if you have an undefined, like the JavaScript, the value technically exists in runtime, but it's just an empty value. That's why it's undefined. So you may create a control flow that will put value in there at some point in time during the execution of the program when the user interact with it. But for locks, that is actually not allowed during execution. So if you have that, the app will exit and then you got a runtime error. So this distinction is huge in language design. Missing mental model. Interpreter is an evaluator of AST. You're thinking scanner, parser, hardware, but missing the center. Core model, AST to interpreter. So the AST this is the nodes or the tree structure that the interpreter convert from string to value. Remember, we convert the value from scanner to a string using from the parser. We convert the token value to string in the scanner syntax tree, and then that syntax tree are now being evaluated by interpreter to turn that string back into a value. So interpreter is a function. So again, interpreter is just a program or a function that maps syntax trees to values. So why errors happens? Because some AST nodes cannot produce a value. So you cannot convert the string of that AST nodes to a value. You cannot interpret it to a value. You cannot apply a function to it. Example, variable node parameter string A. If A not defined, evaluation fails. Subtle confusion, execution versus meaning. You sometimes treat execution equal correctness. So again, why error happens is because some AST nodes cannot convert the string into a value. Example, variable node and then parameter string A. If A is not defined, just like we discussed earlier, then the evaluation or the referential transparency of evaluation will fail because you have that undefined. That's why the locks exit and it has a runtime error. And again, not all language does that. We're just trying to explain how the runtime actually works or how your program exits. Subtle confusion, execution versus meaning. We sometimes treat execution equal correctness, but execution can continue even when meaning is broken, like with JavaScript. So that's the issue. That's why we have this type safety. Sorry. What's that? Static type, statistically type, and dynamically type. So statistically type, it will check this semantics error or meaning error during compile time, so that the app won't exit at runtime, like TypeScript. But in JavaScript, it doesn't actually do that. So the execution can continue even when the meaning is broken. So it doesn't necessarily exit in JavaScript. So some language exit, but some does not necessarily. It just continue even if the meaning is broken. But at least you know that there's some illogical, you know, code there. So what will block you later if not fixed? Key correction: correct execution is not meaningful execution. What will block you later if not fixed? There are the dangerous ones. First, mixing hardware and semantics will break compiler theory type systems. Second, thinking variables equal memory will break closures, scope, functional programming. So since a function has this conditional, control flow constructs in which not all of the code are meant to really run, it only runs if it meets conditions. So variable, thinking that variables equals to memory is a simplistic way of defining, but it's good for beginners, but that's not actually how it works. Third, not seeing evaluation as function will break interpreters lambda calculus. So evaluation, like evaluation of that node, for example, of that to turn that into meaning, not seeing that as just a function or like the meaning that you impose or the program, will break the understanding of how interpreters actually work, because again, interpreters is just a function applied to those AST strings that turns that into a meaning, and then lambda calculus, and when we will go back to lambda calculus in the future videos. Fourth, not distinguishing no value versus a value like undefined will break JavaScript mastery, React debugging. Final corrected model, here's the clean version you should aim for. Program execution is AST to environment to evaluation to value. So this environment and evaluation is what we did, what we will do. So this is the code that we will do in the next future video. So this will be our interpreter environment plus evaluation. Runtime error code occurs when evaluation is the node, no valid value exists. So a runtime error exists if that a function or the interpreter function applied to AST3 and then produces no value. That's what you get, a runtime error. But again, not all interpreter, not all language will exit all or will crash just because one of the AS3 node has no value. Hardware role executes instructions correctly, does not understand meaning. So the hardware role is just a CPU like doing this calculation, fast calculation. That's actually what we do, what the computer do. So that is being, your interpreter turn that into value and then compile that to bytecode, and that bytecode become a virtual machine that could run now or can be compiled into many different hardware. And that hardware, what that hardware is doing is really just performing that calculation. So it's not aware of the location of memory, it's not aware of this runtime, etc. It's just there doing calculation. Language runtime role enforces meaning. It stops invalid computation. So that's what the language runtime. It enforces semantics and stops invalid computation. Final insight, this is the one to keep. You're not debugging what the computer did wrong. You are debugging why the program has no valid meaning under language rules. The hidden connection you're missing, you've been asking, why can't execution continue? What is a runtime error really? Is this about memory or CPU? What does stop unwinding actually mean? This section answers a deeper prerequisite question. What is the program even trying to compute? Key insight from this section, not all expressions produce values. This is the missing piece, your mental model. So the expression, basically what a programming language is just an expression of combination of regular expressions. So not all of those expressions produce values. Like not all of that evaluate or execute na do computation as a computation from CPU. Some are just there to hold value like a statements. Your current model slightly wrong. You're thinking code to execution to value, but assignment breaks that. So correct mental model. There are two kinds of things in expressions. First are values. So here we have 5 and then a string and then a plus b. This evaluates to actual values in memory. So this transform a data to a new data, or sorry, this type of like values evaluates to an actual value. So it is thus the evaluation. There's another one, I dash values, which point to just allocations. So like here a obj.field. So this evaluate to a place in memory or environment, not a value. Deep connection to your earlier question when you ask, why can't execution continue safely? Now the real answer is because sometimes the interpreter expects a location but gets a value or vice versa. So let's say the function applies to the tree node and then the function or the interpreter expects a location and then gets a value or vice versa, expects a location and gets a value. It means the interpreter could not evaluate it, or depending on the rules of the interpreter, if it's JavaScript, it will continue the execution, but for most interpreter, it will not continue the execution of that code and will provide a runtime error. So why assignment is fundamentally different? Example, a equals string value, semicolon. What you thought happens, common misunderstanding. First, evaluate a. Second, evaluate value, string. Third, assign. Wrong. What actually happens, resolve a, find storage location of a. Second, evaluate value string, which gets a value. Third, store value into location. Deep truth. Assignment is not about computing a value. It is about mutating a location. So it's not computing a value per se, like adding 1 plus 1, but rather mutating a location and then putting that value to that location. So your biggest misunderstanding exposed here. You've been thinking everything values is values flowing through memories. This is incomplete. What you're missing, the distinction between value and location. Why this is dangerous for your future learning? If you miss this, you will struggle with pointers, C, references, JavaScript objects, closures, React state, compilers, huge problem.